All right, so quick find is too slow for huge problems. So how are we going to do better? Our first attempt is an alternative called quick union. This is a so-called lazy approach to algorithm design, where we try to avoid doing work until we have to. It uses the same data structure, or array ID with size n, but now it has a different interpretation. We're going to think of that array as representing a set of trees, it's called a forest, as depicted at right. So each entry in the array is going to contain a reference to its parent in the tree. So for example, 3's parent is 4, 4's parent is 9, so 3's entry is 4, and 4's entry is 9 in the array. Now, each entry in the array has associated with it a root. That's the root of its tree. Elements that are all by themselves in their own connected component point to themselves, so 1 points to itself, but also 9 points to itself. It's the root of the tree containing 2, 4, and 3. So from this data structure, we can associate with each item a root, which is representative, say, of its connected component. So that's a root of 3 is 9, going up that root. Now, once we can calculate these roots, then we can implement the find operation just by checking whether the two items that we're supposed to check whether they're connected, whether they have the same root. That's equivalent to saying, are they in the same connected component? So that's some work going to find the roots of each item, but the union operation is very easy. To merge components containing two different items, two items that are in different components, all we do is set the ID of P's root to the ID of Q's root. That's make P's tree point to Q. So in this case, we would change the entry of 9 to be 6 to merge 3 and 5, the components containing 3 and 5. And with just changing one value in the array, we get the two large components merged together. That's the quick union algorithm, because the union operation only involves changing one entry in the array. Find operation requires a little more work. So let's look at the implementation, a demo of that one in operation first. So again, we start out the same way, but now the ID array entry really means that every one of these things is a little tree with one node each, every one pointing to itself. It's the root of its own tree. So now if we have to put 4 and 3 in the same component, then all we do is we take the root of the component containing the first item and make that a child of the root of the component containing the second item. In this case, we just make 4 as parent 3. So now 3 and 8. So again, we take the first item and make it a child of the root of the tree containing the second item. So now 3, 4, and 8 are in the same component. 6 and 5, 6 goes below 5. 9 and 4, so now 4's, the root of the tree containing 4 is 8. And the root of the tree containing 9 is 9, and so we make 9 a child of 8. 2 and 1, that's an easy one. Now if we get our 8 and 9 connected, we just check do they have the same root, and they both have the same root 8, and so they're connected. 5 and 4, 4's root is 8, 5's root is 5, they're different, they're not connected. 5 and 0, 5 goes to be a child of 0. 7 and 2, 7 goes to be a child of 2's root, which is 1. 6 and 1, 6's root is 0, 1's its own root, so 0 becomes a child of 1. Each one of these union operations just involves changing one entry in the array. And finally, 7 and 3. So 7's root is 1, 3's root is 8, 1 becomes a child of 8. Okay, and now we have one connected component with all the items together. All right, so now let's look at the code for implementing quick union. The constructor is the same as the other one. We create the array and then set each element to be its own root. Now we have a private method that implements this process of finding the root by chasing parent pointers until we get to the point where I is equal to ID of I. And if it's not equal, we just move I up one level in the tree, set I equals ID of I, and return it. So starting at any node, you just follow ID equals ID of I until they're equal, and then you're at a root. And that's a private method that we can use to implement the find operation or the connected operation. You just find the root of P and the root of Q, and if you check if they're equal. And then the union operation is simply find the two roots and then set the ID of the first one to be the second one. Actually, less code than for quick find. No for loops. There's this one while loop that we have to worry about a little bit, but that's a quick and elegant implementation of code to solve the dynamic connectivity problem called quick union. So now we're going to have to look at can this code be effective for large problems? Unfortunately, quick union is faster, but it's also too slow. And it's a little different kind of too slow than for quick find. There's times when it could be fast, but there's also times when it could be too slow. And the defect for quick union is that the trees can get too tall, which would mean that the find operation would be too expensive. You could wind up with a long skinny tree of each object just pointing to a next, and then to do a find operation for object at the bottom would involve going all the way through the tree, involving n array accesses just to do the find operation. And that's going to be too slow if you have a lot of operations.